Okay, now I'm going to change the numbers here that these orange points are based on, and you'll see the equation for the line of best fit will also change. Right? So right now it has a slope of about 0.59 and a y-intercept of 1.8. Okay, now I'm going to change the data. Okay, so now you see the slope is smaller, right? The slope is 0.34 approximately. Okay, now we'll make the slope bigger. Okay, so the points are going up at a greater rate, and now the slope is 1.95 approximately. Okay, we can also make the slope negative, right? I'll start with larger numbers and work my way down. Okay, so now our slope is negative 0.52 approximately. We also have a larger y-intercept, right? Because we're starting with a larger number. Okay, so that's the equation of the line of best fit. And you can use that line of best fit to make predictions. Okay, so for example, let's say you're looking at how many hours of sleep someone got. Let's start with 5, and we're going to be adding 0.5 each time. Okay, you know what? Let's start with 4. There we go. So we have from 4 to 14.5 hours of sleep. It might seem like a large number, but it is possible. Okay, and let's say we're looking at a ranking of someone's efficiency. Okay, there's some test that marks people from 1 to 10 that looks at how good their problem solving is. All right, and results looked like this. All right, now I'm just gonna actually delete these orange points. So the blue points, so we're only looking at the orange. All right, and let me format the axis. So instead of going up to 30, it just goes up to 15. There we go. Okay, so a number of people were studied, okay, with different values for hours of sleep. The people who had 4 hours of sleep averaged a 1 out of 10 on this test. The people who had 4.5 hours of sleep averaged 4 out of 10 on this test. People who had 5.5 hours of sleep averaged, hold on, we got a little issue in our equation here. There we go, much better. Okay, people who got 5 hours of sleep averaged 2 out of 10. People who got 5.5 averaged 3 out of 10. People who got 6 hours of sleep averaged 4 out of 10, and so on. Okay, so there is some randomness to the results, as we would expect, but we certainly see a trend, okay, which is that the more hours of sleep someone gets, the better they score on this problem-solving test. Okay, now what is that trend if we take away the randomness? Well, the trend is that line. Okay, that line, which I'm actually going to put here, highlighted yellow. Okay, it has a slope of approximately 1.1, and it has a y-intercept of approximately negative 2.62. Right? And we can graph this line. If we were to graph it, it would be this orange dotted line right here. If you were to continue it to touching the y-axis, it would touch that y-axis at approximately negative 2.62. Okay, and you can use that to now make predictions, right? Let's say people are typically getting 6 hours of sleep in some subset of the population. Well, you can expect they'll get about 3.98 or round to 4 hours of sleep, 4 out of 10 on this test, right? Let's say someone is getting 8 hours of sleep. Well, then you can predict that they would get approximately 6.18, so approximately 6 out of 10 on this test. Now, our actual study showed people getting 8 out of 10 on this test. But when you look at all the other values for other amounts of sleep that people got on that test, and you create a line of best fit, it suggests that that 8, that's actually a result of random fluctuation, and you should actually expect people to be getting 6 out of 10, not 8 out of 10 on the test if they got 8 hours of sleep. Okay? And making that line of best fit, using it to make these kind of predictions, okay, that's what the purpose of a linear regression is. Okay? Now sometimes your data doesn't go in a straight line. Okay, so sometimes your data might look like this. For example, temperature and time. Okay? Right? It might fluctuate. It gets higher and lower and higher. Maybe it's fluctuating throughout the year. Maybe it's fluctuating over the day, between day and night. And a straight line through all of these data points, a line of best fit, would not be very useful, right? So is a linear regression, which is a regression using a line, is it useful in this situation? Well, yes, because if you take a subset of the data, okay, like here, then a linear regression is useful, right? So even if the data does not follow a linear trend, you can still zoom in enough so that it does follow a linear trend. It'll just be a different slope here than it is here, for example. A different slope here, a different slope here, right? If you zoom in enough, it does follow a linear trend. Alternatively, if you zoom out enough, it will also follow a linear trend, often. Okay, so let's say your data is temperature throughout the day. Well, if you look at one day, your temperature might look like that. But if you look at temperature over an entire week, well, that's 7 days, right? So you'd see something that looks like that. So what do we have? 1, 2, 3, 4, well, 5 days. Okay, a work week. Now if you zoom out even farther, right? So if you're looking at, say, not 5 days, but 30 days, well, then you've zoomed out so far that you don't see those bumps for each day anymore, and your data just looks like that. And then a linear regression makes perfect sense, right? So zooming out can make a non-linear phenomena linear, and zooming in enough, right, can make a non-linear phenomena linear for a particular subset of the data. That's why the linear regression is such a useful tool. Now the other value here, that R squared value, that's a representation of, well, how valuable is your linear regression? How well do the data points actually follow this line? Okay, and that R squared value, it fluctuates between 0 and 1. The closer it is to 1, the better your line of best fit fits with the data points. The closer it is to 0, the worse your line of best fit represents those data points. In our case, 0.78, that's pretty good. Anything higher than 0.7 is quite good. Right? Now, let's say I'm going to change the data. Okay, so we still see an upward trend. We still see our slope is 0.7692. It's still a positive slope, but if you look at our R squared value, it's not 0.7-ish anymore. Now it's 0.3-ish, okay, which is a lower value. And you expect a lower value because if you look at the data points, they're now farther from the line. They're not as well represented by that line, right? So if these were your study results, right, you would conclude, okay, yeah, there is an upward trend. People do perform better on this test if they get more sleep, but it's not that significant. It's not as significant as the previous data set we had. The significance, I mean how significant hours of sleep is in terms of how well you perform on the test. Now I'm going to change the data points one more time. Okay. Now your data points are all over the place. Technically it's an upward trend because your slope is still positive. It's 0.2587. Okay. Maybe with the naked eye you can see a bit of an upward slope, but if you look at that r-squared value, 0.0489, it's practically zero, which means you have no correlation. Okay, you have practically no correlation. R-squared, it's hardly ever going to be exactly zero. So what you want to look at, is it close enough to zero? Like 0.1, 0.2, that's very close to zero. Okay, so the correlation here is either very weak or non-existent, right? So if there is an upward trend, which technically there is here, you can't treat that as a significant upward trend, right? It's just a little bit upward due to the randomness, right? It may as well be a little bit downward. No correlation, right? So in this case, the number of hours of sleep someone got does not affect their performance on this test, right? So that's called a negative, no correlation. Now a negative correlation, we'll do that here now. Okay, so now our slope is negative 0.88. Okay, so we do have a downward slope. Okay, it is a negative correlation. But you look at your r-squared value, it's still positive. Your r-squared value is always positive, and actually it's pretty close to 1, 0.8. Okay, so that is a strong correlation, right? It's negative because it's sloping down, but it's strong because your data points are close to the line of best fit. Okay, in other words, your r-squared value is close to 1, because the closer your data points are to the line of best fit, the closer your r-squared value will be to 1. Okay, so anytime you're talking about a correlation between two parameters, for example, hours of sleep and score on a test, in our case, there's the direction of your correlation, which can be negative or positive, right? Or no direction at all, in which case you call that no correlation. And then there's the strength. The strength is represented by the r-squared value. Closer to 1 is stronger, closer to 0 is weaker. And the direction is represented by your slope. A negative slope means negative correlation. A positive slope means positive correlation. And an r-squared value close to 0 means you have a very weak correlation. So regardless of if your slope is positive or negative, you're going to call that no correlation. Okay, just like I'll give you a no correlation situation again. Okay, so here your slope is negative, right? So it could be a negative correlation, but you look at your r-squared value, you see it's so close to 0, that's such a weak correlation, you're going to call that no correlation at all.